Okay, let's begin. Let's pick up with the last example. We did one just before leaving. There's something I wanted to ask you guys to a follow-up question on that. Just to allow something to dawn on you. So, from last example, I believe we were putting in $1,000 per month. We were getting 4% APR. And we were doing that for 40 years, right? And what was the amount that we ended up with again?
1,181,961.
61?
Yes.
Yeah, so it's a way to become a millionaire very, very slowly. Not necessarily recommended, there was just for the purpose of an example. And I wanted to follow up with that. Make sure you can answer this follow-up question. How much of this is actually interest? How much of this was not your own money that you put in? How do you actually go about calculating it? Yeah?
We just subtract 40 years times 12 months times $1,000 from the total.
Right, so you're going to figure out your payments. Now, that you are making $1,000 every month, 12 times per year for 40 years. So that's a long time. So that gave you what?
480,000.
That's
480,000.
480,000. Just flat? Pretty much. So, which means the gain from interest is going to be what? Well, you're going to just take that 1,181,961 minus 480,000. And what do you get?
701,000.
701,000?
961.
961. So over this time period, you actually gained more interest than the money you even put in the first place. Right? That's the magic of compound interest. Just wanted to make sure that kind of dawned on you, right? So yeah, it's you got $1 million, but it's not like you lost $1 million. Technically, it's not like you were sacrificing $1 million over 40 years. You sacrificed 480,000, and you collected $1 million at the end. So you actually it's like someone gave you free money. If you just set this and forget it, it's like having someone 40 years from now just giving you $700,000 for doing nothing. Just wanted to make sure that you knew how to calculate interest. And yeah, that just, whenever a question might follow up and ask you, oh, how much of this is interest, then just figure out how much you're actually putting in and then subtract it from the total when it's being compounded. Okay, I want to just make sure that we have that idea. I wanted to actually, at this point, move on. So, last time, we derived a formula for the future value of an annuity. Remember what an annuity is? It's just a sequence of regular payments that you're making, and we just consider the case where you're making regular payments of a certain fixed amount into an account over time. How much would that amount to at a certain point in the future? We derived that it was that guy, right? And then we actually use that to do this example. One thing I want you to note is we can actually solve for the payment part of this equation. So this would mean that PMT is going to be equal to how would you get that? Yeah?
Just multiply by the reciprocal of the
Right, so you're going to take this and you're actually going to multiply over there. Or, yeah, you can flip this and multiply by the whole thing, or move it in pieces, but just make sure you're moving it correctly. So you're going to end up with the future value times R over N over 1 plus R over N in T minus 1, right? And so this is just looking at the same process from a different angle. Here we figured out if I'm making these payments, how much will I have at some point in the future? But you can also look at it from another perspective. Let's say I know how much I want to have in the future. What should my payments be now? Right? So this allows us to find payments needed for a future amount FE. And this formula actually has a name. It's called a sinking fund formula. This is called a sinking fund formula. Now, not anything too complicated. A sinking fund is simply where
For that one on the left, you see it looks like an H, so.
oh, this is an N.
Yeah.
It's the number of payments. Yeah.
Okay, I'm just a bit confused.
Allows us. Okay. So sometimes you actually know what you want to have in the future, and now you just want to figure out what do I need to start paying now in order to have that in the future, assuming that I reasonably know how to predict the interest rates that I'm going to get. Okay, so that's called a sinking fund. So something like a college fund is a sinking fund. So when you were born, your parents might have decided, oh, you know, in 18 years, I'm going to pay for this kid to go to college. What should I be putting away now so that in 18 years, I'll have all the money there to just send him off to college, right? So that's an example of a sinking fund, and this is kind of a formula that you would use for that. So if you think you can predict the interest rates that you're going to be experiencing for the future, you can use this thing to calculate exactly how much your payments would have to be in order to build up to some value in the future. So let's just go with that example. So the example, suppose in 18 years, they're going to want to have a sum of $150,000 to be able to do whatever with. Maybe send a kid to college or do whatever. let's assume the 4% APR again. Compounded monthly. What should your monthly payments be? So this is a nice formula that helps you figure out what are the payments or installments that you need in order to meet some future obligation. Just decide, I want to have this much money this far from now. What do I need to start paying now in order to make that happen? So you would use the sinking fund formula because what you're talking about here is finding a sinking fund. So you know the future value that you want is 150,000. The payments that you're going to be making, you don't know. That's actually what you want to figure out. You know the interest rate, it's 4%. You also know that it's compounded once per month, so that means n is 12. So this means, and you also know the time, 18 years. So this means, let's see, the payment is going to be future value times r over n divided by 1 plus r over n to the n t minus 1. That's a mouthful. So actually make sure you can plug that into your calculator and let me know what it is. So 150,000 is 0.04 over 12 over 1 plus 0.04 over 12 raised to the 12 times 18 minus 1. What are we getting here?
Yeah, 475, 30.
475? Everyone concur?
I got enough for that.
Yeah, okay. So I will trust you guys. So that's what it's going to cost you to have $150,000 in the future under these assumptions. Just put away $475 a month and you will have that ready in 18 years. It's a nice little thing to know. And of course, this is all kind of speculative. You have no idea for sure that you'll always be getting the 4%, but it gives you a ballpark. You know, it gives you some idea of what you should be aiming for. Here's another way we can use this formula. So by the way, this formula is equivalent to the formula that I gave you at the end of last class. I just solved for one or the other, right? So when I refer to the sinking fund formula, I'm referring to either of these, but it's usually referred to by the one that, they usually mention the one that where you solve for payment as the sinking fund formula. It's got another use. I actually want to talk about that earlier. this together. Because I actually want to talk about a different kind of annuity payment. So let's look at the other side. Let's talk about the present value of an annuity. So here we've derived the relationship between the future value of an annuity and the payments that we're making currently. Now I want to derive the relationship between the present value of the annuity and the payments that we're making. And let's kind of build up to this idea. So now we know so far that if you want to build up to some amount of money, assuming compound interest and a one-time payment, that's going to be the formula, right? So we can think of this as some present value, some that I'm putting into an account now, and using this formula and a given interest rate, a certain number of times being compounded, and a certain stretch of time, I can figure out what the future value is going to be of that money. But right now, I want to focus on this guy, right? So let's talk about the present value of something. This means I can actually solve for the present value by simply dividing both sides by this. Another way to write that is going to be to the minus nt. So by solving for this formula, notice what you're actually thinking about here. You are thinking now, P is how much money I need to invest one time. Remember, this formula didn't deal with recurring payments. We're doing the one-time payment. Now, in order to have $A in the future, T years into the future. So that's a one-time thing. So you can, for example, say, I want to have $1,000 1 year from now. Okay. What lump sum should I put into an account gaining, let's say, 3% APR compounded monthly? So if I want to make sure that at the end of 1 year I have $1,000, what do I need to put up now, right? If I'm thinking of making one payment. Now, obviously over that year, I expect there to be some sort of increase to whatever money I put in. So I can obviously put in a little bit less than 1,000, right? Which is good. I don't want to have to put the whole 1,000 if I don't have to. But what is the present pain that I have to feel now in order to have $1,000 in the future, assuming a 3% compounded monthly interest rate? Okay, go. What do we do here? So A is 1,000, yeah?
R is 0.03, N is 12, T is 1.
Right, and so we're going to use P is equal to A 1 plus R over N to the minus NT. It's going to be 1,000, 1 plus 0.03 over 12 to the minus 12 times 1.
I got $907.
$900.
$70. About 48 cents.
Right? Not really worth it at that point, is it? But you save $30, it's something. But anyway, I'm using this idea to kind of segue to the idea I want. So here's how we're going to expand on this question. Let's say I'm a little bit more ambitious. Now that is a very different question, right? Because this isn't just, well, yes, I'm still putting in a one-time lump sum, but I want to get payouts, multiple payouts of $1,000 over a large time span. That is a little bit more complicated to answer, right? Sure, if I want to know what lump sum do I have to do now to get one lump sum later, that's pretty easy. But what lump sum do I need to put in now in order to have multiple payouts later? Assuming that the whole time that I'm going to be withdrawing stuff, I'm withdrawing $1,000 a month, but whatever is currently there, sitting there, is still gaining 5% while I'm withdrawing $1,000. And the idea is I want that at the end of that 5-year period, no more money's left, right? I want to be able to withdraw $1,000 every month for the next 5 years. Now that's a very different kind of scenario. Let's actually see how to solve that, and then we'll come back to this example. Actually, copy that question down. I think I want more board space here. Okay, do this. So now here's the idea. I need to find multiple present values. I need to find a present value for each one of those payments. And then I want to add them all up. That's basically going to be the idea. So now I'm going to kind of do it in general, and then we're going to actually plug in the 5 years where we actually need it. So let R equals these regular payments that I'm looking for. So here is what's happening. Say we want M payments. So there's a certain specific number of payments that I want to have. Okay? So what's going to happen is that here's the now, right? So at this point I need to invest some money that is going to give me payouts over some time span, right? There's going to be the first period, the second period, the third period, dot, 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 the M minus first period, and the nth period. So I want to have M payouts. I'm going to invest some money now, and then at a certain point in the future, I'm going to take a payment, R. I'm going to take another payment, R. I'm going to take another payment, R. I want to have M payouts of value R over some time period. Okay? So these are the payouts. Always the same number. We're drawing $1,000 every single time for M times. Okay. Now the question is, what is the present value of those payments? Meaning, how much money do I need to put in now so that these guys are going to come to me in the future? So what I will simply do is figure out, what do I need to put in now in order to get the first R, plus what do I need to put in now to get the second R, plus what do I need to put in now to get the third R, and so on and so forth. Now, of course, this guy is not going to have a lot of time to gain interest, so I'm probably going to have to put in more in the beginning than I would for the future one. So that's the idea. So I do expect to be putting in less over time, but I do want to figure out how much exactly that do I need to put in. So what I'm going to do is I want to put in the present value of the first payment. This means I am one pay period into the past. I'm kind of imagining, okay, if I want to have this in the future, what do I have to have now? Well, that's going to be 1 plus R over N to the minus 1, right? Using the formula that I just solved for the P, right? The R is like the A here, right? So interest would have been applied one time to whatever this thing is to give me that. Interest is going to be hit twice in order to give me this one, R over N. Here, this thing is going to be hit with interest 3 times, right? So whatever I put in now, interest is going to hit it 3 times by the time I need it, and so on and so forth. So for here, I'm going to be hit by interest minus M minus 1 times by the time I need that, and here I'm going to be hit by interest M times, right? So if this is the money I started with, taking that as the P in the A formula, it's going to be hit with 1 plus R over N raised to the M, which is going to give me the R as the result. So that's what it looks like. So ultimately, the present value, what I have to put in now, is going to be the sum of all of these. So now we're kind of going to do the same trick that we did last time. So I'm going to call this equation 1, and I'm going to create another equation that I'm going to subtract from it. So let me multiply this by 1 plus r over n. Now if I multiply this by 1 plus r over n, they cancel, that just gives me r, plus this is going to cancel, that's just going to give me to the minus 1, plus that's going to cancel, and that's going to give me to the minus 2, plus this here is minus m plus 1, so if I multiply that, it's going to be minus m plus 2, plus, if I multiply this, I get r times 1 plus r over n to the minus n plus 1. And call this equation 2. And now what I'm going to do is I'm going to take equation 2, subtract equation 1. So this minus that is going to give me what? Well, it's going to give me r over n times pv. Now, we are going to create some duplicates here. So there's no r in the top row, so I'm going to have r minus whatever. So the r is going to stay here. But now what's going to happen is notice that this will get subtracted. This minus that, that cancels out. This minus that, that cancels out. The next term here is going to cancel this term. This guy is going to cancel the thing before this. This is that, so this is going to get canceled and that's going to get canceled. So pretty much everything gets canceled except the first guy here and the guy here. So this is going to be minus, because I'm subtracting that, r times 1 plus r over n to the minus m. That is equation 2 minus 1. And so now, let's actually solve for the present value. So this means that my present value is going to be equal to r times 1 minus 1 plus r over n to the minus m divided by r over n. Now, again, using the change of notation, just to make things a little bit more clear. I'm thinking of the R as the payments that are being made to me. So R I'm going to replace with PMT. I know how to count the number of periods, that's just going to be n times t. So this is 1 minus 1 plus r over n to the minus nt divided by r over n, and of course this here is p. So that is the formula for the present value of an annuity. So if I want to have a bunch of payments, regular payments, that formula tells me how much what lump sum I need to put in now. Yeah, do you have a question?
Yeah, is the PMT divided by R over N or no? In the
Yeah.
Okay.
Either way, it'll be the same. Because if it was separate, you can think of it as being over 1, and then if you multiply the fractions, you'll get the same thing. So you can put it on the top or leave it separate, you should get the same thing. It's just very important that you remember that parentheses should be around these two. Once you remember those parentheses, then either interpretation is going to work. Okay, so now using that formula, let's answer the question before. How much money do I need to put into an account so that I can sit back and receive $1,000 every month, I said, for 5 years? You don't need to know the derivation, you just need to know the formula. Just thought I'd show you where it came from. Like I said, I'm never going to ask you to derive anything or prove anything here. But I just don't like giving people formulas without any context. Just weird quirk of mine. So, yeah, so back to last time. Okay, so tell me how we're going to apply that here. So tell me how the values in the last problem, how they're going to be used in this formula. Who's who here? I know the payment should be 1,000. What else do I know?
R is 0.05.
And it's 12.
T is 5.
That's all we need. I love how everyone pitched in a different value. Why our powers combined? Okay. So now the PV is going to be equal to 1,000 times 1 minus parentheses 1 plus 0.05 over 12 raised to the minus. Don't forget that sign. The negative in the power is super important. Otherwise you might get a negative answer or something like that. So yeah, if you get a negative answer, just remember that that's probably where the mistake happened. You forgot to put a negative sign on the power. N times T. So there will be 60 regular payments ultimately. And then we can divide that entire thing, or just even divide this part by 0.05 over 12.
It's 52,990
52,990.
and 71 cents.
Yeah, that's a lot of money. Follow-up question. How much money did this save me?
$7,009.41.
So yes, that's a big lump sum, but I can get away with 7,000 and change here. And again, in the grand scheme of things, probably that's still a lot of money. But like I said, compound interest, it needs some time to get going. Right? So 5 years is nothing. Like you really start to see the dividends over 20 years, over 40 years. So. Yep. And how did you actually come up with that number? Let's make sure that everyone understands. Because the payouts would equal to what? You want 60 payments of $1,000 each payment. Right, so the payouts will total 60,000. Right? So you paid 52,900 in order to receive 60,000. Right? You paid to get back more money. So under this condition, what is $60,000 worth to you 5 years into the future, spread out? Well, it's worth $52,000 right now. If you can pony that up, you can get that. Now here is another, so we saw just now that PV is equal to payments times 1 minus 1 plus r over n to the minus bt over r over n. We can solve the payment again, just like in the last time we could solve for a payment. And in this case, we would end up with the payments would equal to present value times R over N divided by 1 minus 1 plus R over N to the minus NT. Now, this formula is called the amortization formula. Why is it called the amortization formula? Because to amortize debt, that's the phrase used here, means to pay it off. Kind of for a morbid reason here, because the root mort means death, right? You know, like mortal. So basically you use this formula if you want to kill a debt, right? That's kind of was the language used here. It's called amortization. Now, how is it that we're using this to kill a debt? Well, we just thought, I thought I was paying this money so that things would get paid to me. So here's the thing, here's how that works. When you go and you borrow money from somebody and they charge you interest on that money, and they tell you, okay, you can pay me back in fixed installments. What you have to realize is from the loaner's perspective, what they're doing is they're giving you money now so that you can pay them in the future, right? So you're over here, to you it's a loan, it's a debt that you're paying down, but to them, it's like they're putting up a present value of money in order to get a future amount of payments, right? So from the loaner's perspective, they're trying to compute the present value of an annuity. It's just that you're the annuity, right? So you can actually look at this from the flip side, and once you do that, you get the amortization idea. Right? So pretty much, a loaner is just going to look at you and kind of try to assess you. If I give this person this much money, and charge them this much interest, will they be able to pay me back these fixed payments over this period, right? And here's how they would actually calculate the payments based on what value they're willing to give you at what interest, right? So you come, oh, I want to get a $100,000 loan. That's going to be PV. They're going to decide what interest they want to charge you based on your credit score and other factors. And then that's going to tell you the payments that you have to make. And then they're going to have to decide, is this person capable of making these payments over the long term, right? And that's why when you try to borrow money, they kind of ask you, how much do you pay for rent? What are your expenses? What is this? What is that? Because then they're going to take your income, they're going to take out all the expenses, and they're going to see, does this person have enough money to make this payment every month, right? So all these calculations, these are the things that are happening, right? And this is the formula that's working in the background, right? So let's actually do an example of that. So this is just the previous formula where this formula that we derived, I just solved for the payment part of it. And once I solve for that, it's called the amortization formula. If I solve for payment in the formula I derived last time, that's called the sinking fund formula. Because they're used for very different purposes, which I'll talk about in a little bit, just to make sure that there's no confusion. let's not name anybody, is offering you a loan of 100,000 at 3.99% APR, compounded say monthly. So someone is willing you to lend you $100,000 on these terms. What would your payments be if the loan term, right, that means the length of the loan is 5 years? And you're required to pay fixed installments. Another common place where something like this will be used is, of course, like with something like a mortgage, right? You get a mortgage, someone lends you the money to buy a house, which is usually going to be a lot, 500,000, something like that. And they're charging you a certain percentage. They're going to plug it into a formula and figure out what your monthly mortgage payments would be. This is the formula that they would use. And then they're going to have to determine, can this person actually afford that payment? And then if not, they might lower the loan amount to something that's more applicable. So I'll give you a couple minutes to try that one. I think the question mark here. Yeah, do you have an answer?
1,841.0.
Okay, tell me how you got it.
Well, PV is $100,000.
That's what they lend you right now.
Then R is 0.0399. N is 12, and T is 5. And then just 1 day.
So we're going to need the payments. That's going to look like EV times whatever n over 1 minus 1 plus r over n to the minus nt. So that's going to be 100,000 times 0.0399 over 12 over 1 minus 1 plus 0.0399 over 12 raised to the minus 12 times 5, which is 60. And you said you calculate this was
1,841.
800?
1,841.
And what?
2 up.
2 out? Okay, you can borrow 100,000. Just pay back. You have to be paying back 1,800 a month under these terms. Questions? Yes.
Yeah, so in all these examples, are we assuming that like the payment is in the same interval as whenever it's compounded? So like if it's compounded monthly, is the payment always gonna be monthly?
Yeah, and well, no, but for this question. But usually, you assume the periods start as soon as you put the money down, so it starts right after, because that's usually how loans work.
So are we ever gonna have to do problems where like it would be like compounded monthly, but you make weekly payments or something like that? Or like that, well, that wouldn't make a difference, but I guess the other way around or something like that, like compounded weekly, but you make monthly payments or anything like that?
Yeah, so what you would do in that situation is, which I probably wouldn't ask that, but if I do, what you would do in that situation is you would convert your weekly payments into monthly payments. You'll turn your payments to coincide with the timing of the interest.
Oh, right.
Right, so let's say you're paying $10 a week, you'll just think of that as $40 a month.
Oh,
And then use the 40 as the payment. Here's another way you can use this formula. And I think I want the first version here. Okay, and that was the one that says PV equals PT. We can use this to determine the max, short for maximum purchase price of a commodity or whatever. So here's what I mean. So this is basically the calculation you would go through to make sure you're not living outside your means. Okay. So, example. Say you want to get a car, right? After budgeting, you determine that one struck a chord. You want to buy a car? So I want a car. He's talking about me? This is actually really weird to do backwards. think that's okay. Okay, so let's say you budgeted, okay, I know how much is going to food, I know how much is going to rent, I know how much I'm putting towards entertainment, I know I'm putting towards blah, blah, blah. And I know how much I'm putting towards saving because I have that long-term plan going on. I gotta put $1,000 so I can be a millionaire in 40 years if everything else goes wrong. And so you determine you can afford $450 per month to pay for a car, right? And you might, that's just the purchase price. You're not worried about insurance or anything. You actually calculated how much you'd get for insurance or whatever. And you might be able to lump insurance into this if you think of it indifferently, but I want to keep it pretty simple. You can afford $450 per month in car payments. Now, let's say car dealership is having a special, no credit check, so they don't even care. No credit check, you just need a job. So you show up, show them a pay stub, and they're like, yeah, we'll give you a loan, whatever. You know those guys, you've heard the commercials. Right? So assume you have a job, you're making enough so that you can spare $450, right? They will charge, it's like a special, so super low price, 2.99% APR. Say compounded monthly. For 5-year loan. So if you take a loan from these people, you just have to pay off the car payments in 5 years, and they're offering 2.99% APR and no credit check. So normally, car dealerships, like I said, they charge simple interest usually, but no credit check. Just show up with a pay stub. We don't ask any questions. Okay, all right. Maybe I'll take a bite. So let's assuming you plan on buying from these people. What price should you negotiate for the car? Right? So before walking into this dealership, you need to have a price in your mind. I cannot pay more than this because I can only afford $450 a month. So when you go in and you ask for a loan, how expensive can that loan be, assuming that you do not want to live beyond your means? What's the maximum purchase price? What's the number you have to get them down to, or just you definitely need to choose a car that's below that amount? We'll just start this one because I want to make sure we can wrap up on time. So basically I'm going to use the present value. So the payment, that's determined, right? I can only do $450 a month. That's not going to change. And a 2.99% interest. And compounded monthly, and the loan lasts 5 years. So this means, what can they loan you in the present so that you can make those payments and pay them off? Well, that's going to be $450.
$25,049.76.
Gotta get a car for 25,000. Go beyond that, now you're just gonna get yourself into debt. Like debt you actually can't manage. I mean, you're getting into debt anyway, but you can manage this debt. You've done all the calculations. You know, okay, $450 a month is safe, right? That's the price you need to get. So either just aim for a car that's lower than that, or aim for something a little higher and try to, haggle. But that's the number. You can't walk away with less than that number. And by the way, remember that car dealership, they always add on fees at the end, right? So they'll negotiate a price, and then after the fact, oh yeah, there's this fee in for warranty and blah, blah, blah. And sometimes they don't even tell you about it, right? They'll give you a printout to sign. You need to make sure that that number on the thing is less than that. So now, because the variables used are similar and even the formulas are similar between the sinking fund and amortization formulas, I kind of want to make sure that there's no confusion when you want to use which. So if you're in a test and there's several questions, some of them are amortization and some of them are sinking funds, how do you not get confused? So let's look at sinking funds versus amortization. And some common differences. So based on what the goal of the problem is, you should know which formula you should be using. So sinking funds. This means you're making regular payments now to receive lump sum in future. Versus, usually something's happening like there's a lump sum now and regular payments in the future. This is usually happening when you're saving up money for some future goal. This is when you're paying down debt. Or looking for payouts that start and end on particular time interval. So they all have very similar variables, so I just want to make sure you know the difference. When you're reading a problem, you have to figure out what's the goal here. Am I saving up to something, or am I trying to pay something down? Right? If you're saving up to something, the sinking fund formula is what you should be using. If you're trying to pay down something, the amortization formula is what you should be using. So here you're doing regular payments now to have some big lump sum coming to you in the future, versus I'm putting down a lump sum now to have payments being made in the future. And debt becomes when someone else puts a lump sum on you so that you pay them in the future. So that's kind of where the difference is. And you should also notice that these ideas can be mixed and matched. You don't ever even have to do one or the other, sometimes both. And so here's an example. Now this isn't something I'm recommending. In general, I think this is a bad life plan, but just for you to see what I mean. Suppose you're 20 now, right? So that is the current state, right? You plan on working for 40 years. So at some point in the future, there's going to be a 60-year-old you. At this point, you want to quit your job and live off your savings for a certain period of time. Let's say all the men in your family die when they're 80 or younger, right? So just statistics, right? Don't